Hello. In this video we're going to be looking at writing what I'm going to call, even though this is writing equations of motion, writing vertical equations of motion. This is a very important concept with where we're going. Again, I guess maybe let's look at the idea behind what we're doing. We are taking a problem, hopefully you've seen this, where'd it go? Okay, we're taking problems, and I guess I just need to, there we go. All right, let me start a new page. We're taking problems like this. Eventually we're going to take some sort of object. I'm throwing things, but you can't see that. We're going to take some sort of object, a ball, like a baseball. Let's say there's a baseball, and I give you a vector. A baseball gets hit, and it's going to go 15 meters per second, and the angle is going to be 15 degrees. Okay, fine. We want to know when is that ball going to, at one point we're going to know, okay, we know this ball is going to follow a trajectory. It looks kind of like this. We want to know the specifics though. When is it going to get to the maximum height? What will the maximum height be? And we want to know the range. Where is it going to hit over here? Where will the baseball land? And in order to do that, it's kind of a complex process because you have up and down and side-to-side motion all mixed up together at the same time. So what we're actually going to do is we are going to split this up. And we're going to pretend that there are actually, instead of one baseball, there are two baseballs. One ball is going to be strictly describing how it moves up and down. And so we're going to imagine that vertically, the vertical positions are determined by a ball that's moving up and down. And we can figure out what this is. This is going to be our vertical component of the velocity. So real quick, you have that equation for Vy, I is going to be equal to V times the sine of the angle, right? So if this is 15 degrees, then this component is actually going to be equal to 15 times the sine of 15. And if I plug that into my calculator, it tells me it's about 3.88. So let's call it 3.9 meters per second. So there's one ball that goes up at 3.9 meters per second. And there's another ball that is going to go to the side. Another baseball that all it does is go horizontally. And it's going to travel the horizontal component, which of course Vx is what we'll call that. And it's going to be equal to V times the cosine of theta. Again, this is all from the previous video, so you've done an assignment on that hopefully, and you understand how this works. We're going to take our velocity, 15 times the cosine of 15, and I get, looks like 14.488, we'll call it 14.5. So these are the components. In essence, this baseball will be moving, this blue baseball will be moving with the same type of motion as both of these at the same time. So if you imagine a baseball just thrown straight up in the air at 3.9 meters per second, if we can determine how it moves straight up in the air and then comes back down, that will be the height at any given time. This will describe the height. This baseball is just going to move at 14.5 meters per second, and this is going to describe its like horizontal position. How far will it be from where it began? And so we're going to have to use these two ideas together to sort of figure it out. In essence, what we're doing is we're taking a two-dimensional motion, right? We're taking two-dimensional motion. This is what it's actually doing. It's actually going up and down and side to side at the same time. And we're taking that two-dimensional motion and turning it into two one-dimensional problems. We have a up and down problem that's one-dimensional, and another side-to-side problem that's one-dimensional. And these are much easier to deal with. You don't have to worry about doing it all at once. Here you just do it separately and then combine them when you need to. That's the general idea. So let me go back and let's talk about vertical equations of motion. That's what we're trying to write. So we only care about the up and down part right now. Earlier in class we discussed how everything accelerated at the same rate. All objects on Earth, assuming there's no air resistance. And we are going to assume there's not air resistance because it makes it kind of tough. And so we said it's negative 9.8 meters per second squared. Of course, the negative is because it falls down. And this is the acceleration to Earth. All objects on Earth are going to accelerate towards the middle of the Earth at 9.8 meters per second squared. And this is because of Earth's gravity. A larger planet like Jupiter, on Jupiter, the acceleration due to gravity is actually 26.0 meters per second squared, and a lot higher. And on Pluto, it's like 0.6 maybe, off the top of my head, I don't know. But the point is, larger objects have more gravity, smaller objects have less, and so the acceleration due to gravity is going to change. Well, a while ago, sorry, I know this is kind of off. There we go. So previously in the last unit, we had an equation that looked like this. So we're talking about velocity and acceleration. We know there's an acceleration, right? So that's the point I'm getting at. Up and down, there is an acceleration, and it's the acceleration due to gravity. We have this equation that look like this. We have velocity would be equal to the initial velocity plus a times t. And this was an equation that kind of told us, okay, what will the velocity be of an accelerating object? Well, that is what's happening to an object that I throw up and down. If I throw an object, it will start to fall back down. In other words, it is accelerating because of gravity. So we can actually change this equation, right? It doesn't change a lot. We're specifically talking about the vertical velocity, Vy. And this is going to be equal to the initial vertical velocity. Again, we're only talking vertical right now. So this is more specific than this equation. Plus the acceleration. But what is the acceleration of an object that's moving up and down, or an object that's accelerating due to gravity? All right, that was my Dora the Explorer pause. Hopefully you said negative 9.8. And you're correct. Symbolically, I guess I should write symbolically. You're correct. It is going to be negative 9.8. But it is g times t. So I guess this is a more general form. This would work for all planets, instead of just Earth. But this is the equation. And so this is really what you want to write down. This is all the nice parts. So we have the vertical velocity is equal to the initial vertical velocity plus g times t. Now, very important, by the way, all these problems are going to be for Earth. We're not going to do any problems, although it would be kind of cool to do problems for Jupiter or Pluto. Maybe we will at some point, but we're not going to do that now. For now, all the problems are for Earth, so we'll just say g is negative 9.8 as far as you're concerned. Now, this is, again, make sure you write this down, but this is our equation for the vertical velocity. This component, by the way, this component is the vertical component of velocity. It is not the entire thing. So if I went back to my problem, remember we had 15 meters per second, and that was at 15 degrees. In this case, Vy is only the vertical component. It's this piece right here. It's what you find using the sine. It was 15 times the sine of 50, which was 3.9. So in this case, if I was writing an equation for that object, right? So let's think about our baseball. For that object, the equation would look like this. Vy would be equal to, okay, Vyi was my component. So to find this, again, I'll write it out. It was 15 times the sine of 15 degrees. And when you plug that in, you got rounded, but about 3.9 meters per second. So this is going to be 3.9 plus gt. Well, g is negative 9.8. So instead of putting plus negative 9.8 t, although you could, I'm just going to put minus 9.8 t. And this is the vertical velocity equation for that scenario. In other words, this thing describes the velocity of that object at any time. You plug in a time, and of course it has to be in seconds, but you plug in a time for t, and you will get a velocity back out. Okay, let's see. What is the velocity at 2 seconds? Well, if I want to know the velocity at 2 seconds, it would just be 3.9 minus 9.8 times 2. Let me see what that is. 3.9 minus 9.8 times 2. And I got negative 15.7. So obviously it's traveling down at that point. If you plug in 0, you'll get positive 3.9, which makes sense. That's what it was going originally. So this is a very powerful equation, a very powerful statement. You can plug in any velocity and you can get a time. Conversely, you can plug in, at least what we did. We plugged in a time and got a velocity. But you could also plug in a velocity and get a time. What will the velocity? When will the velocity be equal to? I don't know. I'm just gonna make something up. When will it be equal to 1? We'll just plug that in for velocity. 1 is going to be equal to 3.9 minus 9.8 times t. And then you just solve for t, right? So this is just algebra. I could subtract 3.9. So 1 minus 3.9 gives me negative 4.9 equals negative 9.8 times t. And I think you actually get 2. Or it's going to be close. Or 1/2. It'll be 1/2 maybe. But I think it's 1/2. Yeah, exactly 1/2. So your time gives you negative 0.5 meters per seconds. Seconds. It's time. So you see what I'm saying? The time at whoops, I divided on my calculator. I didn't divide by negative 9.8. It will become positive, which makes sense. It should be positive. You get 0.5 seconds. The point is at 0.5 seconds is when it's going. So this works both ways. You can plug in a velocity and get a time, or you can plug in a time and get a velocity. It's an equation that works. All right. Next one is our vertical displacement equation. Again, we had a displacement equation last time, and it looked like this. X is equal to xi plus vi times t plus at squared over 2. This was, again, from the last unit. This is our displacement equation. We can adapt it for vertical displacement. It's a bit more specific, though, right? Instead of just displacement, it's vertical displacement. I'll use y since it's up and down. Equals, it's still the initial vertical displacement, or what you would really call the height, right? The initial vertical displacement is a nice way to say height. There's supposed to be a plus sign. Plus the initial velocity, again, that's going to be our vertical velocity. So still using that sign component. That's why being able to find that component is so important. The acceleration, again, is the acceleration due to gravity, g, t squared over 2. A bit nicer is here. And so you can write this down. Again, it's the initial height is really the important. It's the initial height plus the initial vertical component. Don't forget, that is actually v times the sine of the angle. Very important you understand that. It's your initial velocity times the sine of the angle. So go ahead and write that down. You can pause if you need to. So let's apply this to our baseball again. Now, if you go back to what I was talking about the baseball, there is no initial height given. There's not. Okay, so then yi is going to be 0. Just like previously, there wasn't a displacement given at 0. Sometimes there will be given 1, sometimes it won't. So 0 plus the initial velocity. Again, it's the component. So we did 15 times the sine of 15, and we got, again, 3.9. You see this number coming up over and over and over again. It's very important you understand how to get that. So 3.9 times t minus 4.9. Oops, I'm getting ahead of myself. I apologize. Let me erase this. Minus 9.8, because that's the acceleration due to gravity, or g, t squared over 2. Well, this can simplify, right? So I have negative 9.8 times t squared divided by 2. In PEMDAS, you can do multiplication division in any order. So I can go and divide this before I multiply by t squared. Understand that only the t gets squared. Now that I do have to square first before I can multiply or divide. So I'm not going to bother t squared. But I can take negative 9.8 and divide by 2. And this is going to be a number that you're going to see a lot. So I'm just going to drop the 0. No point in writing it. 3.9t minus 4.9 t squared. So negative 9.8 divided by 2 gives me 4.9. And this happens a lot because g is always going to be there and 2 is always going to be there, right? It's not changing. G is going to be negative 9.8 and 2 is going to be 2. And negative 9.8 divided by 2 is going to be negative 4.9 every time. So this is an equation that describes the height. You can think of this as the vertical displacement equation, the height equation. Again, this is a very powerful statement. Let's see. What is the height at 0.5 seconds? So what is the height at 0.5 seconds? Well, if I want to figure that out, it's going to be 3.9. So I'm going to have to hurry because I'm running out of time. Minus 4.9 times 0.5 squared. And of course, you can always pause videos. 3.9 times 0.5 plus negative 4.9 times 0.5 squared. And just quickly, I think I did it right. I got 0.725 meters. So it would be 0.725 meters in the air at 0.5 seconds. What happens if I put in 2 seconds? Well, you're going to see I'm going to get a negative, which means it's actually below the ground, which makes sense. Eventually, it's going to come back to the ground, right? 3.9 times 2 minus 4.9 times 2 squared. 3.9 times 2 minus 4.9 times 2 squared. Yeah, I get negative 11.8 meters. All right, I'm running out of time, but these are the equations of motion, and you'll see there's an assignment. But basically, you just figure out the components. The key is this middle part must be the vertical component on this one and on this one. All right, thank you for watching.